Hello. Today we're going to go through some gas stoichiometry. Hopefully you've been keeping up and all this e-learning is working for you pretty well. So let's get started. Let's go right here. So what this will deal with is applying the gas laws knowledge that you've learned into stoichiometry problems. So let's talk about the situations where this might come up in. So we know that if you have moles of a substance, you can certainly convert to liters of a gas. If the problem is at standard temperature and pressure, we simply use the conversion 1 mole of gas equals 22.4 liters. If, though, the problem is not at STP, that is not at 25 degrees Celsius, not at 1 atmosphere of pressure, then what you're going to do is solve for moles of substance. And then once you know the moles of the gas, you will plug that into the ideal gas law, PV equals nRT. And I will demonstrate that for you with several problems. When you have a problem that's at non-STP, there's going to be, the problems will look like one of two different types. Either you'll be given the liters of gas, and then you'll have to start with ideal gas law, or you'll be looking for liters of gas in which you'll have to start with a stoichiometry conversion. And again, that might not make sense at this point. After I go through it, you'll see that those are the only two ways we can work the problem. I suppose it's like saying you can drive the car in going forward, or you can put it in reverse, and those are the two different ways you can drive a car. So let's look at our first problem. So it says, what volume of carbon dioxide gas forms when 5.25 grams of calcium carbonate are decomposed at 103 kilopascal and 25 degrees Celsius? So the first thing that I noticed about this problem is that it's not at STP. Standard pressure would be 101.3 kilopascals, and this is certainly not then standard conditions. So therefore, let's see what we need to do. Well, if you remember with the stoichiometry problem, you need to start with a balanced chemical equation. So let's begin there. So we're starting with some calcium carbonate. In fact, we're starting with 5.25 grams of calcium carbonate, and we're going to cause this to decompose. A quick way to cause this to decompose is to simply heat it up. That's what the triangle means. Now, I'm not interested in how much calcium oxide I'm going to produce. I simply want to know what volume of carbon dioxide gas I will get. And of course, this is not at STP, so I'm not going to be able to use the 1 mole of gas equals 22.4 liters. So my strategy is this. I'm going to, if I'm looking for liters, I'm going to first calculate the moles of carbon dioxide that I would produce. Once I get the moles, that is, do the stoichiometry, then I can use PV equals nRT to find the volume. So here we go. I'm trying to find the moles of carbon dioxide that would be produced from the decomposition of 5.25 grams of calcium carbonate. My first step would be to convert grams to moles. The molar mass of calcium carbonate is 100 grams per mole. And then using the coefficients from the balanced chemical equation, for every 1 mole of calcium carbonate, I will produce 1 mole of carbon dioxide. And the units work out so that this gives me 0.0525 moles of carbon dioxide gas. Now, I know that doesn't answer the question, but again, what we're going to do is, once we find the moles, now we're going to calculate moles into volume using ideal gas law. So let me go to a new sheet of paper and remember what we've got here. So it's the same question, and I wrote down the given information. We had the pressure from the problem. We had the temperature. Remember, you have to add 273 to get that to Kelvin. And I chose a value of R that corresponded with the kilopascal unit. Now, the N was not given in the problem, but remember, that's what I just calculated based on my 5.25 grams of calcium carbonate. Next, if I know the pressure, the N, the T, the R, I'm going to solve for volume using ideal gas law equation. This is the only equation we can use when we have number of moles or grams is ideal gas law. So PV equals nRT. Now, I would generally solve this for the volume. Volume is nRT over P, and then plug in. This person has chose just to plug the numbers in. That's fine. And so we'll go ahead and do that. We know the pressure. We put that in. Volume is what we're looking for. We know N, we know R, and we know T. So we can solve that, and we get our final answer for the volume of carbon dioxide gas produced under these conditions would be 1.26 liters. That's all we have to do. Let's try a few more of these. All right, let's slow this one down a little bit. So here's the question. How many grams of aluminum oxide are formed? So aluminum oxide, that's a product, are formed when 15 liters of oxygen under these conditions, 97.3 kilopascal, 21 degrees Celsius, are non-standard temperature and pressure. And then we must assume that we have plenty of aluminum. It must be in excess. Okay? Now, we're trying to find a mass. So the strategy says, if we're given liters, which we are, start with ideal gas law and calculate the moles of oxygen. And once I know the moles of oxygen, then I can solve for grams of aluminum oxide. So I'm going to write down all the given information. I'm given the pressure in the problem. I'm given the volume. I'm given the temperature. And I just reflexively add 273 to get that into Kelvin temperature. Always convert Celsius into Kelvin when doing gas laws. And again, I chose the R that corresponds to the pressure in kilopascal. So at this point, I can choose my equation, the ideal gas law, PV equals nRT. I'm going to take all of this information on the left side and substitute it into the equation, solving for number of moles. So I'm solving for the moles of oxygen, and it comes out to be 0.597 moles. Now, based on 0.597 moles of oxygen, I can get the mass of aluminum oxide. I'm going to go to a new sheet of paper to do that. So we took this information and we determined that 15 liters of oxygen under this condition corresponded to 0.597 moles of oxygen. Now I'm going to do regular old stoichiometry using the coefficients from the balanced equation. 3 moles of oxygen goes on the denominator, will produce 2 moles of oxygen on the numerator of aluminum oxide. So that didn't line up very good, but it should say 2 moles of aluminum oxide on top, 3 moles of oxygen on the bottom, moles of oxygen cancel. And then finally, I need to figure out what 1 mole of aluminum oxide weighs, and it weighs about 102 grams. 2 aluminums times 27 grams plus 3 oxygen times 16, that's where I'm getting the 102 grams. Moles of aluminum oxide up here and down here cancel like that. And I get my answer to the question, 40.6 grams of aluminum oxide. All right, let's try some more. I'll choose some of my own problems here for you to do. And just stay with me. I know this is a little bit challenging for some of you, but if you just practice and listen and watch and then rewatch, it's going to make a lot of sense to you. So let's look at this question here. It says, find the volume of hydrogen gas made when 38.2 grams of zinc react with excess hydrochloric acid. And then we're given some conditions that are clearly non-STP or non-ideal. So the first thing I'm going to do is write out my equation, and I'll go ahead and balance it. So I have zinc metal reacting with hydrochloric acid. This is a single replacement reaction where the zinc replaces the hydrogen. Hydrogen is dumped out as a diatomic hydrogen gas, and I produce zinc chloride. Zinc is a 2+ ion, chloride is a 1-, so this is the correct formula. I went ahead and balanced it by adding a coefficient 2 in front. Next, I like to write all the information from the problem into or around the equation. So I'm trying to find the volume of hydrogen gas. I'm starting with 38.2 grams of zinc. I have an excess amount of HCl, which means basically I could ignore the HCl for the purpose of the problem. I'm not being asked about the zinc chloride, so I can ignore that as well. Now, we're given that this gas is not at STP. It's under this new temperature and pressure. So the thought process is, how do we begin? If we have a mass, do we try to get to a volume? Well, let's think about this. We're starting at zinc, we're going to hydrogen gas, starting at mass, and we're going to a volume. Now, to go this way and take 3 steps to do this would tell you that the gas is at STP. Well, it's not at STP, so that may not be the best approach. But let's go ahead and see what we can do. Let's start this anyway. Let's figure out the volume of hydrogen gas if I start with 38.2 grams of zinc. My first step is to convert grams of zinc to moles of zinc, and that's pretty easy. I looked at the periodic table. 65.4 grams of zinc is 1 mole. Grams of zinc cancel, like that. I'm sitting right here now at moles of zinc. How do I cross the middle bridge? Excellent. You said use the coefficients. So how about 1 mole of zinc produces 1 mole of hydrogen? I agree. 1 mole of zinc, 1 mole of hydrogen. Moles of zinc cancel, like that. Now, if you were to take it one more step and say 1 mole of hydrogen is 22.4 liters, this is, if it was at STP, you get this answer. But it's not at STP, so that's not what we should be doing. Okay? So that's what it's saying here. If it's at STP, we can use that last conversion. 1 mole is 22.4 liters. But we're not at STP, right? We're at 88 Celsius and 107.3 kilopascal. Now, there's a couple things we can do. We could use the combined gas law, and I'll come back and show you that method next. But instead, maybe, let's do this. Let's figure this out. Let's say we got how many moles of hydrogen? It's 38.2 grams of zinc. Let's start the same way. 65.4 grams of zinc is 1 mole. I'm just repeating what I've done here. And then finally, 1 mole of zinc is 1 mole of hydrogen. If we stop at this point, we get moles of hydrogen gas. Number of moles of hydrogen are both temperature and pressure independent, meaning once you know the number of moles, the temperature and pressure won't change those. So now what I can do is use PV equals nRT. I know the pressure, I'm looking for the volume, I know the number of moles, I know R, and I know T. So I'm going to go ahead and solve that for volume. I like to do my algebra first, and I'm going to substitute in all my values. So the number of moles I just calculated, 0.584 moles of hydrogen. I chose my value of R in kilopascals because the pressure was in kilopascals. And I also added to my 88 Celsius 273 to get that into Kelvin temperature. Substituting in my pressure, all the units cancel here except for volume. And volume comes out in the unit I'm looking for here. That'll be liters. And so the answer here is 16.3 liters. I think for most students, that's how they prefer to solve the problem. They want to take the mass, convert that into grams, the mass from grams into moles, and then use ideal gas law. That would be my recommendation. The other way we could do this is to use the combined gas law. Let's just go ahead and just entertain that thought for a moment. If we use the combined gas law, oh, maybe my link's not working there. I guess we won't worry about that method right now. Oh, I guess it is. Now it's working. I was there. Okay, so let's look here a second. Pardon me. So the initial pressure would be standard conditions would be 101.3 and 273, and we're trying to find that volume under those conditions. Remember, that's when it was 13.1 liters. That was the initial way we solved the problem. And then we'll say, well, let's look at and make this pressure, 107.3, pressure 2, and this temperature, 361 Kelvin, T2. So P2 is 107.3 kPa, and T2 is 88 Celsius, but I have to remember to add 273, So that's 361 Kelvin. And the only thing I don't know then is V2. Now, because V1 was in liters, V2 will come out in liters. Now, you've done this type problem, combined gas law, P1 V1 over T1 equal P2 V2 over T2. And again, I'm just substituting in all of these numbers and units into this equation. And to solve this, I'm going to cross multiply and divide. I assume you can do the algebra. And when you do that, you get the exact same volume that we got earlier, 16.3 liters. Doesn't matter to me if you use this using combined gas law or if you use ideal gas law after you solve for moles. Whichever makes more sense to you is the method I would prefer that you use. Let's see if this makes sense a little bit. We made the temperature go from 0 Celsius to 88 degrees Celsius. What should that do to the volume? Well, it should make it go up because the molecules are moving faster. And sure enough, and the temperature went up, it went from an initial volume of 13.1 liters up to 16.3 liters. Now the pressure, that's a harder one to consider because the pressure actually increased. And if you increase the pressure of a gas, it should decrease the volume of the gas. So in this case, it's a little hard to guess what's going to happen to the new volume. Would it go up or down? But sometimes it's worth thinking about. All right, that was a fun problem. Let's try another one. Keep our brains sharp during this COVID-19 isolation time. Because sometimes doing these problems really helps take your mind off other things. So here we go. What mass of solid magnesium is required to react with 250 mils of carbon dioxide gas under these conditions? That carbon dioxide gas is at 1.5 atmospheres and 77 degrees Celsius. And a chemical reaction will proceed that will produce or yield solid magnesium oxide and solid carbon. First thing we have to do is write a balanced chemical equation for that. So we're starting with some magnesium, solid, and we're reacting that with some carbon dioxide gas. And it looks like we're going to produce some magnesium oxide. Magnesium is a +2 oxidation charge, oxygen's a -2, so MgO. And then we're going to get solid carbon. How would you classify that reaction? If you said synthesis, that's not quite right. Single replacement, you've got it. You got an element and a compound, and that forms an element and a compound. Next, let's go ahead and put all the information into the question. So what I'm seeing here, I reread that question to myself. Well, I guess I'll go ahead and balance it first because I know I can't do a chemical stoichiometry problem without balancing everything first. So now we have it balanced. Now we'll go ahead and put in the given information. I'm looking for what mass of magnesium, so X grams of magnesium. If I start with 250 milliliters of carbon dioxide, and I have to remember this is not at STP, okay? So the volume, 250 milliliters, what am I going to have to do with that in order to make that a useful unit? Good, we have to convert that to liters. So you said that's 0.25 liters, I agree. What other information do we have? Read the question again. All right, we have the temperature. It's 77 Celsius. I heard you. Convert to Kelvin by adding 273. So that's 350 Kelvin. And then go ahead and put the pressure in. Good. Now I can leave the pressure at 1.5 atmosphere, but then I have to pick the right value of R. Okay. If I always want to use the value of R of 8.314, then go ahead and convert that into kilopascal, although it's not necessary. The conversion would be 1 atmosphere is 101.3 kilopascal. So I simply multiply 1.5 times 101.3 kilopascal. Now, look at what's happening here. I've got a volume of a gas not at STP, so I'm probably going to use ideal gas law. I'm going to solve for number of moles. I know pressure, I know volume, I know temperature, and I know R. So I can plug everything in. There's my pressure, my volume, my temperature, and because my pressure is in kilopascal, I'm using 8.314. If you were wondering, you could have left your pressure on the numerator as 1.5 atmosphere, and then on the denominator, you would have used 0.0821 liter atmosphere per mole Kelvin. In any case, you'll get the same exact value for the moles of carbon dioxide, 0.013 moles. Now, that's not what the question's asking. The question wants to know how many grams of magnesium. What we've done so far is figure out how many moles of carbon dioxide gas I have under these conditions. So now I'm going to do a regular stoichiometry problem. I'm simply showing you real quick. If I instead, the 159.95, if I went ahead and left that as 1.5 atmosphere, I would have to change the R value and make that 0.0821 liter atmospheres. In either case, I end up with the exact same value for moles of CO2. Now we're trying to go from moles of CO2 to mass of magnesium. So we're starting at CO2, going to magnesium. We're starting at, remember, moles right here, and we're going to mass up here. So it should take 2 conversion steps, using the coefficients to go from moles of CO2 to moles of magnesium. And once we have that, moles of magnesium to mass of magnesium. Again, hopefully all of these skills, all of these ideas are things you've seen before. We're just getting to put all those big ideas together. So I always write, what am I looking for? X grams of magnesium equal to, what do I know? 0.013 moles of CO2. My first step, crossing the middle bridge, always utilizes coefficients from the balanced chemical equation. So how about 1 mole of CO2 on the bottom will react with 2 moles of magnesium on the top? Again, getting those coefficients from the balanced chemical equation. Moles of carbon dioxide cancel like that. And if I stop now, I'm sitting right here at moles of magnesium. I need one more step. I need to go from moles to mass. So I quickly looked at my periodic table. 1 mole of magnesium weighs about 24 grams. Moles of magnesium cancel. I type this all in my calculator, 0.013 times 2 times 24.3 divided by 1 divided by 1, and that equals 0.63 grams of magnesium. And that's the answer to that question. Hey, these are kind of fun, aren't they? Well, I think they are. All right, let's try another one here, see how this one goes. How many liters of chlorine gas are needed to react with excess sodium metal to yield 5 grams of sodium chloride under the following conditions? And you can read them on the screen. So I started by writing a balanced chemical equation. 2Na plus Cl2 goes to 2NaCl. I'm trying to find out what volume of chlorine gas I need to produce 5 grams of salt under these conditions. Temperature 25 Celsius, pressure 0.95 atmosphere. Clearly not at STP, so I'm not probably going to use 22.4 liters. So the first thing I might do is, now it says how many grams of chlorine equal to 5 grams. Now that's not what it says here, it says liters. Why would I go to mass? Well, let's see if this makes sense to you. I'm going to convert grams to moles. Sodium weighs 23 grams per mole, chlorine 35.5. So 1 mole of salt is 58.5 grams. So those grams cancel. Now, using the coefficients from the balanced chemical equation, 2 moles of salt will be produced from every 1 mole of chlorine gas. So those moles cancel. And finally, 1 mole of diatomic chlorine gas weighs 71 grams. Now, I'm not going to substitute in 22.4 liters to get volume. We already said it's not at STP, that won't work. So instead of doing that, well, I guess if you're forcing us to try this, if we were to do this, then this is going to require us to use combined gas law. P1V1 over T1 equal P2V2 over T2. So we knew the initial pressure was 1 atmosphere at 273. That's standard conditions. And under those standard conditions, where 1 mole is 22.4 liters, it would be equivalent to 0.957 liters. But for our problem, the new pressure is 0.95 atmosphere. The new temperature is 25 Celsius or 298 Kelvin. I can solve for the new volume. So I'm going to plug in all of this information, cross multiply and divide, and I get the volume, 1.04 liters. Again, that might not be the way that I would initially solve it, but again, I want to show you multiple ways to attack these problems to see if they make sense to you. Let's try the ideal gas law method instead. So if we look here, initially it said how many grams of chlorine equal 5 grams of salt. 1 mole of salt is 58.5 grams. Grams of salt canceled. From the equation, 1 mole of chlorine produces 2 moles of NaCl. Moles of salt canceled. And I would have been left with, at that point, 0.0427 moles of chlorine. I then would use the ideal gas law, PV equals nRT, solving for volume, because that's what I'm trying to find. Volume is nRT over P. Now, I know the pressure for my problem is 0.95 atmosphere. I know the temperature is 25 Celsius or 298 Kelvin. And I'm looking for the volume. And I chose an R this time that corresponds to the unit of pressure in atmosphere, so 0.0821 liter atmosphere per mole Kelvin. And I just solved for number of moles. So now I can take this information and plug it into my equation to find out the volume. It's equal to the number of moles times the gas constant R times the temperature in Kelvin divided by the pressure. And look at there, I get the exact same number, 1.04 liters. So as I've mentioned before, there's more than one way to skin a cat. You can solve a problem in more than one way. Whatever way works for you is the way I want you to be doing these. All right, that is the end of our show for the day. I hope that makes some sense, and I will tell you have a good day and take care. Okay, send me emails if you got them. Bye-bye.